Hi everyone, welcome back to Math 256. This is Scott. Let's get started. The agenda today is to continue where we left off and look at how the geometric understanding of differential equations can lead us to the numerical side of things. This is 1.4, analyzing equations, by which we mean, of course, differential equations, numerically. All right. So here's the basic idea. So we can't solve all differential equations. That's a sad fact of life. And even when the techniques of solving the differential equations are ones that we can work out, sometimes we'll get solutions that we can't solve for y, as we saw in the last example. So what that means is we need to figure out a way to get some values of a solution without necessarily getting the formula for the solution. And so what we are going to do is approximate. Approximate solution curves by a sequence of connected line segments. All right. So just to start with, we'll look at what is the most basic technique, and it's basic in two senses. Number one, it's the simplest to do, and number two, it forms the foundation for all of the more sophisticated methods that we will also look at. So this is Euler's method. So this is Euler, as in the famous Euler, the great figure from the 18th century, who developed so much of the foundations of the math that we do today. So basically, here's the setup. The setup is we have a first order differential equation. And we'll just say dy dx equals, and here we're just going to have some expression that involves x and y. Okay, so, and an initial condition. Which we'll just say is two values, x naught, y naught. Okay, and then choose a step size. H. And as you might guess, the smaller the steps, the better. All right, so here's how it works. So let's just suppose here that what we had was, let's say the point right here was the initial condition. Okay, so now the idea is we want to go from that y value to the next y value. And let's say that's one step. And the way we will make the line segment is just by taking the slope that the differential equation tells us would be the slope at this point. So we just go like that. So that would be the next point in our sequence of numerical values. Now then, the slope here, the slope would be m equals, and you just basically plug in the first point that you had, into the differential equation. Because after all, differential equations give you slopes. They give you the slopes as a function of the x and the y values. And essentially here, that will give us then a way of carrying the one value over into the next value. And the next value, we'll write x1, y1. And then the actual numerical value of the x1, y1, well, x1 is just going to be the original x plus h, the step size. And then the new y value is just going to be the old y value plus the slope times the run. Because remember, slope is change in y over change in x, and the change in x is just h. So then what this is going to give us is that the y value is just going to go up by the step size, which is the run, times the slope. We can just call this m naught. Then we would continue to just iterate this over and over again for as many data values as we wanted. So then to continue this, to iterate this process, xi plus 1 is just xi. So in other words, we're saying next x value is previous x value plus h, and y I plus 1 is equal to previous y value plus h times mi, where mi equals whatever the differential equation would produce at the ith value. So this is just going to be x1 or xi, I mean, yi. So it's very simple to implement this. This would be done in modern computing with just a simple loop. You can just proceed with this for however many steps that you want, and you would just calculate it along the way. So just as an example here, let's just say that we took dy dx equals just x times y. So this is a separable differential equation. We would be perfectly capable of finding an analytic solution to this, but it's a good one to start with just because it's a relatively simple equation with, and we can then just see how this would track out. So let's see what we would get here when we do this. So let's say that x naught, y naught. So our initial conditions will just be 0 for x and 1 for y. And then let's say that the step size here is just going to equal, we'll just make it equal to 1. And so this is a very crude step size, but it's good enough for us to just get started with. All right, so then if we want to If we want to evaluate this, if we want to carry out this process, the easiest way for us humans to organize it is with a table. Of course, computers wouldn't really necessarily make a table. They would just, compute value after value in the simple-minded way computers like to do things. But we humans, we need things to be a little bit more laid out for us. So let's just make a table here. We'll just start with I to mean which point we're on. So it's going to be 0, 1, 2, 3, 4. And then let's see. So actually, maybe this is too simple-minded. Let's make h equal to 1/2, just so that way we get a little bit more of the nuances that we can have to worry about here. So then xi, yi, and then let's say mi, which we can actually just plug in here. It's just xi times yi. And we'll just proceed. So one piece of this we can just directly start filling in without even thinking. So we can say the x values are just going to be 0, 0.5, 1, 1.5, and then 2. Now the first y value is known to us. That's equal to 1. And here we can just do the multiplication, and we get the slope. It's just going to be 0 times 1 equals 0. Okay, so the slope is 0, which means then that we are going to be adding 0 times h to our previous y value. So from this now we're able to get the next y value. So it's equal to 1. And we'll just put a little commentary here. I'm not gonna supply the details of every step in this. That's the whole point of laying it out in a table. But basically here, just gives us that. Okay, so now we're able to compute the next slope, which is going to be 0.5 times 1, which is just going to be 0.5. Okay, so then we take our previous y value, it's 1, plus h times the previous slope. So it'll be 1 plus a half times a half, so 1.25. Oops. So double asterisk. So we've got 1 plus 0.5 times 0.5. Okay, and then we can just proceed again, figure out what the next slope will be, and use that to get the next y. And that's the process. So the next slope will just be this times this. And that will then lead us to our next y value, which is going to be 1.25 plus half of 1.25. So I'll just calculate it again. So h times 1.25, which we can just pull out just any old basic calculator, nothing too fancy necessary here, and just crunch the numbers. Times have to be a hero here. And we get 1.875. Okay, and then we can just take the y value that we just got, multiply it by the corresponding x value, get the new slope, and we get 2.81. And here I'll stop annotating each thing. 2.8125. And then here I just take the previous y value, 1.875 plus 0.5 times 2.817 or 8125, and you get this as our final y value for this table here. So 3.28125. I'm running out of digits here, so I'll just round it to 3, or sorry, to 2, I mean. Just because of limitations on the width that I made for my table. But then whenever you're done, you don't have to continue calculating the new slopes, and this would be the basic process. And what's going on here geometrically is if we have a slope field, which I'm not going to draw out the whole slope field here, but let's just say that this was our first condition, our first value here. That's all we need here. And at the very first point here, the slope field would have indicated that it was flat, and so we'll just take its word for it and project it out to here. And then the next point that we were looking at, the slope field would have told us that there was a slope of 1/2. So then we'll just obey that and go out to here. And at the next point, the slope field would have told us that there was a slope of 1.25. So we'll just take its word for it and go out to here. And then the next point would have said that, according to the slope field, that there was a slope of 2.85, so it'd be a relatively steep slope, and we'll go out to here. So this is what the sequence of the solutions would look like. Now, where does the error come in on this? So the error comes in because we are actually going to either be falling ahead or falling behind or jumping ahead of the actual values, depending on how much the slope changes over the course of the interval. So errors come in. So errors come in when the slope changes drastically. It doesn't even have to be that drastic, really. Over the intervals. Now, this is actually a worse thing even than it sounds, because what's going to happen is you are relying on an erroneous value to generate your next erroneous value, which in turn will lead to another erroneous value, and the errors will accumulate in any of the methods that we're about to discuss. So the errors accumulate the further out we go. All right, sad but true. What can we do about it, though? So the way to reduce the error So reducing the error, there are a couple of ways that we can do that. So one way is reduce the step size. And this is true for all methods. So this is true for all methods. The problem though is if your method isn't that great, then you won't get a lot of payoff for this. And this method is very basic. It is just the foundational method, and it's not going to give us a very precise, it's not going to give us very accurate answers in the long run. And so this is okay, but better. The better method is to come up with some other way of getting the slope that takes into account the change in the slope over the course of the interval. So change. How slope is estimated. Okay, so that's the way that actually this problem has been dealt with most effectively, both historically and currently. And that is where the more sophisticated methods come in. So more sophisticated methods fall into a family of what are called uh, Runge-Kutta methods, named after two scientists who, at the turn of the 20th century, both basically independently of each other, used the methods here. So Runge-Kutta methods, or RK. So what is frequently called just the improved Euler's method, or there are other names like Hoyne, another German mathematician, in fact, who also developed this, would be RK2. So the idea here is instead of just taking the value at the beginning of the interval as your estimate of the slope, take the average of the beginning and the end of the interval. So use the average of the slopes at the beginning and the end of a line segment to estimate the actual rate of change. So graphically, what this would look like is this. So let's say we had this as our initial condition. And let's say that we knew the actual solution curve looked like this. So again, we don't know what the actual solution curve looks like. So let's say this is the actual. The actual solution curve. And let's say that this was our initial condition, and let's say that Euler's method led to, so this is h, our first point here. Now what we can do is we can take the slope of this one and basically take the make a new line. So this is the old, let's say this would be the old y1, and what we can do is take the average of this and the slope from that point forward, and what that does, and then just cut that interval in half, and that gives us a new y1 here. And then we would repeat the process. So we would say from here, okay, maybe the slope is going like this. And we just proceed. And you can see that it's closer to the original curve. Not dramatically, but pretty close. And then to actually implement this, we will use so we'll take K1, just a letter different than Ki. This is just a letter different than M. So Ki is equal to just f of xi yi. So this is like classic Euler method slope. And then we can use, so this is classic Euler's method slope. Use this to get an estimate of the new y value. So this is going to be old y value plus h times Ki. So this is first draft of new y value. And then one more letter, we'll just say L. It's another letter that's like M, but different. So Li would be f of the next x value and the projected y value here. And then finally, Mi would be the average. 1/2 Ki plus Li. So this would be the slope at the end of the interval, of the original interval. And then this would be our modified slope estimate. And that's what we would use finally to get the new. So sorry, my camera cut out for a second there. So what I was saying was we get a modified slope estimate by taking the average of the classic Euler slope and then the slope that we would get at the end of the interval. And then we get a new y value by doing basically the same process as before, just with the new slope. So this is the revised new y value. All right, now to see this actually in practice here, let's just take we're not going to do a lot of this one by hand because it's more cumbersome and computer. And so let's just get our hands dirty with a small amount of actual calculation by hand. This isn't something that we typically would do by hand because it becomes a little bit ungainly, but just so that we know what's going on when this is done for us. Let's just take differential equation x plus y. Let's just take as an initial condition. So another way you can write the initial condition is in this form, which is good to see a variety of these things. So there's the initial condition, y of 1 equals 1. And let's just say h equals 1, just to make things nice and easy as much as we can. All right, so we're just going to make our table here. I'm not going to make a lot of entries in our table, again, because it is a bit time consuming, as you're about to see. So we'll just say I, xi, yi. So right now already, I is 0. We can see that x is 1, y is 1. That's our initial condition. When I is equal to 1, x will equal 2. And then if I equals 2, x will equal 3. So we'll just flesh it out this far. Okay, now what are the components that we're going to need to generate here? So first off, there's ki. This is first draft of the slope. So we just use the differential equation and the x value and the y value here to get this. And then there is going to be our projection of what the y value would have been just using the classic Euler's method. So that's going to be 1. So previous y value 1 plus not 0.5 plus 1 times the k1, and so that's going to equal now 3. All right, and then on the basis of that, we can now find the next estimate of the slope, which, remember, this one is you take the next x value and what was supposed to have been the next y value, and you plug those into the differential equation. Okay, so that's going to be 2 for the next x value plus 3, which is equal to 5. And then finally, we get our real estimate of the slope, which is half of the two previous estimates of this, or half of the sum of the two previous estimates. In other words, the average of those two numbers we just generated, the L and the K. So that's going to be equal to the average of 2 and 5, which is 3.5. And that in turn is how we get the next y value. So the next y value is going to be previous y value plus our new slope times h. And if we wanted to continue the process, we would just proceed along the line. So k, this is the original, the OG slope. You just take x plus y, and that's going to be 6.5. This is going to be where the new y would end up if we were just doing regular old Euler's method. So it's 4.5 plus 1 times the slope, 6.5. That's 11. And then this is going to say, okay, if we take that seriously, then let's see what the slope would be at the end of that interval. So then that's going to be, now we take the next x value in line, which is going to be 3, and we add to it the projected y value of 11, and that gives us 14. And then finally here, what we have is the modified final draft of the slope, which is the average of the two previous slopes, which is 0.5 times the 6.5 plus the 14 gives us a new modified slope somewhere in between the two previous ones. One estimate was way down at 6.5, the other estimate was way up at 14, and so the average of those is our best bet here, 10.25, and then we can use that to get the next y value. So then the next y value from that would be 4.5 plus 1 times 10.25. That'd be 14.75. So as you can see, it's a little bit more of a workout than the classic Euler's method was. The advantage of it is that it incurs a lot less error as it proceeds along. So let's then see. We're not going to actually do this one by hand. This one requires even more calculation that is not very productive for us to just do with a little handheld calculator. But let's just see what the RK4, the top of the line in differential equations, numerical analysis, what it's fundamentally based on. So this is the best family of methods. There are some ways this can be optimized for certain circumstances, but generally this is the top of the line. So the Runge-Kutta for order 4 method uses a weighted average of estimates for the slope. In particular, essentially what it does, if we want to look at it geometrically, is it takes the interval from 0 to h, or whatever the starting x value is, and it cuts it in half, and then say this was our starting one. What it does is it takes first the Euler estimate, putting you out to here, and then what it does is it takes, like, then the next order one out to here, and then what it does is it basically does like an improved Euler's method to get a better estimate of the slope out here. So basically, whatever the slope of that line is, and it uses that to project out to here. And it's very complicated to try to sketch schematically. You won't see very many schematic sketches of this, but essentially the basis for the formula is highly related to Simpson's rule. For numerical integration. And if you want the exact details of it, they are available in your book. But it suffices to say it's a complicated method, but the good news of it is it's a very, very accurate method. And while it's complicated for humans to do and complicated for humans to understand, once you boil it down into a code, computers can do it very, very, very efficiently. So we'll see what this looks like in just when we switch over to to the the Sage applets available to us. But for now, let's just say it's complicated. So it involves very very sophisticated pattern of estimates that it takes into account with a certain very very scientifically determined weighting. All right, so let's just call that that. All right, everyone, let's have a look at doing some of these numerical techniques online using the Sage math program. The easiest way of actually doing that is through the textbook. So if you go to the textbook and you go to section 1.4, section 1.4, and you scroll down to the very end. So here's all a description of the same things we were just talking about. And here, by the way, is a description in more detail of the RK4. And as you can see, it gets to be rather intricate. All right, so we scroll to the very, very end, and you get to a place where there are a bunch of Sage scripts available for you. So if you want to do Euler's method, so here, this would be Euler's method for x times y. These are the initial conditions. So here, down here, it explains the syntax of it. So these are the initial conditions, and this is where the x's are supposed to end. So if I wanted to reproduce the table that we already made, I can put in x times y instead and evaluate. And here you go, a table of values generated by Euler's method for x's going from 0 to 5, step size 0.5, and an initial condition of x equals 0, y equals 1, and x times y for the actual differential equation. So this one is there if you just want to make a table, and you'll notice it gives a gratuitous number of digits. Now, if you want to not just have a table, but you wanted to actually make a graph of it, then you can then change the differential equation, and you go down to this next one here. And what it does is first it generates a list of points, and then it names the points and makes them red, and then it adds lines to them, and then it prints. So here we have exactly as we thought we would have. We have a sequence of line segments, and because they grow so exponentially fast over here, it's hard to see the earlier ones. But what's basically happening, here, I'll make the values a little bit tamer here. I'll make them only go from x equals 0 to 3. Okay, so then what we have is just at each stage, the slope of the next line segment is dictated by what the slope was at this point, what the differential equation said to use for the slope. Now, let's say we wanted to use one of the Runge-Kutta methods. So there isn't a program available on this for the RK2. So that's the one that we worked out. But there is the RK4, which is, of course, the premium top of the line system for the for differential equation finding. And what this is doing, let's say, so evaluate this. So again, I changed the differential equation to match ours. What this is doing is that complicated little calculation that uses the weighted average of a bunch of different components, 4 components in particular, that each can go into the estimate of the slope. And so the same x values here lead to these y values, and we can see it's quite different from what we got over here rather rapidly. So these are the initial conditions right here, and so that's all well and good, but it doesn't make any sense until we see the graph of it. So let's just look at the graph of this and see how good of a representation it appears to be. So we evaluate this and we look at the graph, and again, it's a little bit here. Let's cut the endpoints down just a little bit here to make it more visible. So if you look at this, you can see that it truly is going with the flow of this slope field. It, based on its complicated numerical weighting of the different values that are being compared in making the slope, it really is getting a good representation at any given point of what the slope is for any particular interval. And so it gets a good average, and it ends up making a very pleasant graph here. All right, so this is just a quick little rundown of some of the things that your textbook is willing to give you, but there are actually some other resources. So if you look, for example, just in Google, if you just Google like Bluffton, BLUFFTON, differential equations, a nice little slope field applet comes up, and you can put into that these things very nicely. So you can put that. And if you want to put in an initial condition, you can choose what the method you would use for it. So improved Euler, that's RK2, also known as Hoyne's method. And then Euler is just classic Euler, and we'll just make it 0.5. And we'll submit. What are these x values? That's good enough. The y values we'll want to be a little bit bigger. Let's go x values from -3 to 3. Y values from -10 to 10. And hit enter and submit. And that is what Euler's method produces for you. And if we want, we can zero in a little bit more on it. So this is just looking at it on a more restricted window. Make that a little bit bigger here. Okay, so this is Euler's method and what it does. So essentially, what it takes is at any given point, it takes literally what the differential equation says the slope should be, and projects that out for the whole next step. Now, if you switch instead to the improved Euler method, then what you can see is that now, instead of trying to find what the slope was at that one point, it compares the slope at that one point with what it would have been if we continued, and it takes an average. And so what it ends up doing is producing something that fits along the pattern a little bit better. And if we go to Rungakuda, we can see that this actually, although it looks very, very pointy on its line segments, it actually is keeping up with the curve pretty well. And if we go down here, you can look at actual tables of the values of the function according to each of these methods. So here, this was still the Rungakuda. If we do the improved Euler, it will look like this. And if we were to do just Euler, the table would look like this. So what we have here are tables that you can make, and also just some graphs that you are able to produce in order to get a little bit of an idea of what's going on here. So again, with Euler's method, I'll just make it even a little bit smaller so you can see it more clearly. So what Euler's method is literally doing is making a line segment here whose slope exactly matches what the slope field says, and it just continues that line segment until the end of its step, and then it just goes according to what the slope field would say, and it continues that until the end of its step, and so on. Whereas with Hoynes' method, or the RK2, instead of going like exactly in parallel with the slope field here, it takes what the slope field would have led us to, which would have been right out here, like classic Euler, and it takes that, and it takes the average of these two slopes to make this slope. And another way graphically of seeing that would be if you were to draw this out a whole nother step, then it would be this segment right here. And that looks pretty good. So it looks like a pretty good approximation of where we should be by now. And then it would just repeat the process. So here it would take the average of this slope and where that slope would lead you, and uses that. And then for RK4, similar concept, but more complicated execution. It takes a complicated weighted average, and you can see that it is keeping up with the curve much better than either of the other two. So this one is going to get outstripped by the curve if we let the x go out too far. So we can see that it's falling drastically behind the curve as we go out. Actually, I need to make this even bigger. So you can see it quickly falls behind the curve. Euler falls even further behind the curve. The Rungakuda keeps up with the curve pretty well. So we've got some different options depending on how easy we want it to be and how accurate we want it to be. All right, well, that's going to do it for us playing a bunch of computer games in order to solve differential equations. So this has been your dose of Math 256 for the day. I'll see you next time. Till then, bye.